All right. Hi, everyone. Thanks for attending. So today I will be presenting to you a little bit about my research on WebAssembly, what it is and what I find it interesting. So I'll go real quick with an intro because there's a lot of things to cover. It's a pretty big subject. So I'm Chris. I go by Hugsy on IRC and Twitter and forums. I'm currently a researcher for Sophos Labs in Vancouver. So normally the WebAssembly stuff is not the kind of thing that I do. I'm mostly interested in low-level stuff, so operating system and assembly and breaking stuff and exploiting them. But the reason for this research was mostly that I observed that there's kind of a disconnection between people that say, yeah, I've heard of WebAssembly, and people who actually know, yeah, do you know, can you tell me in detail what is assembly? Yeah, I'm not really sure what it is and how it works. The problem is today, WebAssembly is everywhere. It's, if you have a device, like if you have a web browser, a modern web browser, you are WebAssembly capable. So yeah, it's definitely something that is worth checking out. A quick word about what we'll cover today. So this is the introduction. We'll go through a brief history of WebAssembly, see where it's coming from, because there is a reason and a good reason for WebAssembly. Well, reasons actually. Then we'll cover the specification, version 1.0, as it's called the MVP, which has nothing to do with Microsoft Most Valuable, but it's that's the acronym that they decided. And we'll spend a long time covering the attack surface, because that's what I do, that's what I like, that's I believe what you like as well. Is does WebAssembly weaken or strengthen the security of web browser? And then we'll cover the future and conclude. What we will not talk about is everything that is not web browser related. So I'll just have like probably one slide just to show that it's possible, because WebAssembly is its own environment. It's not web specific, but it was designed for web browsers. But just so you know, this kind of thing exists. So yeah. Okay. So if you've been using web browsers long enough, those acronyms probably look familiar to you, and if they don't, it's okay. But let's go a little bit back in time. So back in '96, Netscape came up with this really good idea. How about we have some code running on a web browser on the client side? Which was a good idea. So that's how JavaScript came to life in the first place. And then we realized that JavaScript is actually terrible for performance. It's really good for interaction with users, but performance it's a disaster. And by design, it's kind of very hard to make it better. Although, yeah, JavaScript engine developers are doing a pretty good job at it. And so we've had a lot of different technologies coming up. If you know some of those logos, then yeah, some of them are quite interesting and original ideas. But they were not really successful. And they had one very, very bad issue, which is they were quite hard to control from the web browser. So the way it used to work the way it still works actually for Java, applets, and Flash, and so on, is that the web browser would just spawn a process that would be the Flash player and so on, and give the data, the code to execute directly to this process. And then it's kind of hard to have both. To have the web browser saying, yeah, okay, what you're doing, I don't really like it, so I'm going to stop the execution, something like that. It's more of a one-shot thing. And probably the worst thing, especially in the web environment, is that it's all proprietary. So it's not a standard. But in 2010, some engineers at Google, working for the Chrome team, came up with this really, really interesting idea, which is called NACL, which stands for Native Client. The idea behind it is to have native code, running in a sandbox. So they said, JavaScript is bad for performance. Let's have code that can actually execute at native speed for your machine, but is not totally overexposed so that you cannot, for example, launch some syscall and pop up some calc or whatever. And so it was really good. It's a really good idea, a really good technology. But the problem is that it never became a standard, and it's Chrome specific. So we don't really like that. Still a good technology, and the performance were there. So then we had ASM.js, which was an idea from Mozilla. So if you've read JavaScript code and you've used this useStreet syntax, that's part of what you're using. It's asm.js. So it's a subset of JavaScript that is going to optimize the code so that you can run it faster. But even at the fastest level, performance does show that it's usually around twice as fast as native JavaScript. So it's okay. It's still a good idea. It's a performance improvement, so that's good. But we are really far from native performance like what we had in Knuckle. And this standard is more of a big hack around JavaScript, because again, JavaScript is really hard to integrate for having better performance. And that's why the three major web vendor companies, so Mozilla, Google, and Microsoft, came together and worked for about 2 years on a unifying standard. So it's a W3C standard. The specification is out there, it's open, which tried to combine all the best between the lessons from the past, so Knuckle and asm.js. And what it is, in the end, is you've got this virtual machine that will be running specific code that can be reinterpreted by the web browser to produce native code. We'll see that in the detail. But it's a fully contained environment that will be running in your browser, a totally dedicated VM which has its own file format and its own instruction set. And it was good. Like, it was really, it is good. So in March 2017, after 2 years in the making, it became a standard. So that's what the MVP is now. So for MVP, which stands for minimum viable product. And it was designed to be minimum enough so that it's a good subset to start with, but it's viable. So you can already start using it and create your own WebAssembly application. And it's working pretty good. You're starting already to have some video games that are being ported to WebAssembly. Just last week, I saw this tweet about someone who ported Vim to WebAssembly. So that kind of shows you what can be done in the future. And it's everywhere. Today, about 75% of all web browsers downloaded on your phone, on your web browser, is supporting WebAssembly. So it's definitely not something that can be left out, and it's like a technology that's going to die. It's actually quite the opposite. The development is quite active. So in a nutshell, we've got, it ticks all the boxes. So all the problems that we used to have on asm.js and Knuckle are all gone. Now we've got a standard, so something that's open for everybody to implement, re-implement, play with. And we've got close to native performance. So yeah, that was a pretty good deal. But how fast is it exactly? So I decided, one of the first part of my research was, I saw all those article, blog posts, WebAssembly is 30 times faster than JavaScript. So that strikes me, and I decided to run my own test. So I created several files, so C file, JavaScript file, and WASM file, that would execute code, which is purely computational. In this case, I re-implemented SHA-256 in C, compiled it in WebAssembly, and had the same done for JavaScript. And the results were, I was the first surprised with those results. I don't know if you can see, but the WebAssembly is way faster than JavaScript can ever possibly be. And on top of that, if you start comparing how fast it is with native PE being executed without speed optimization enabled in the compiler, you can see that it's actually very close. So if we're enabling those speed optimization, then it's going to be a bit more. Well, the difference will be a bit more. But without those optimization, yeah, it's fast. It's really fast as long as you're staying in the computational area. So as long as you're doing pretty much only math and there's low level of interaction, which WebAssembly cannot handle. And it's not just for the web. So this is the slide that I was mentioning earlier. This is showing you that some people have decided to use WebAssembly in a lot of other different areas. You've got some dedicated virtual machines. So if you decide to have your C file, write your own printf hello world, and have it executed natively, you can use the WAV VM that is going to do that for you. it's embedded in smart contract on the EOS technology. And one of the most surprising thing for me was it's now, you can also use it in WinBag. So if you're familiar with the Windows debugger, since the version 10, they've decided to include Chakra Core. And the result is that now you can have WebAssembly that will be running inside the JavaScript engine of Chakra, which is running inside with debug. I have no idea what to do with that, but you can still do it, and that's pretty cool. So now that I hope that I've convinced you with how awesome WebAssembly is, I suggest we move forward and start actually looking at it and see what it is. So we'll be talking about the MVP, the minimum viable product, which, once again, took approximately 2 years to be completed. And the idea behind it was to have a virtual machine that is Turing complete, that has a specific amount of instruction. In this case, the MVP states 172 instructions declared that will perform all kinds of arithmetic operation along with control flow manipulation, memory, load and store, and so on. And the virtual machine itself is stack-based. So it's a little bit similar to Python, for example. You won't have any kind of register. It will be a little Indian virtual machine and with 4 gigabytes of linear address space. Interestingly, the virtual machine does not, well, the WebAssembly format does not understand what pointers are. So in this way, it's kind of awesome because it's going to be killing a whole bunch of vulnerabilities, but also of exploitation techniques straight in the egg. And they will be using the VLQ, which is variable length quantity, for representing the data in the WASM format that we're going to be covering. But first, let's have a look at the instructions. As you can see, that's a subset of all the instructions, but it's a pretty good summary to give you an idea. It's very basic. It's like, yeah, kind of a RISC environment. And it's all those instructions are, do not, as you can see, do not have any syscall. There is no way of interacting with the system. That doesn't make sense on WebAssembly as far as web browsers are concerned. The only caveat to that is those instructions, the two last instructions, grow memory and current memory, which kind of allow a way to allocate another page, or to ask for the JavaScript engine to allocate another page to the WebAssembly engine. But besides this, it's pretty much only done for computation because there is no syscall, there's no interaction way. So pretty simple again. So what does it look like? A WASM file. You're going to have a header, which is 8 bytes, always. Start with null byte, followed by ASM, and then the standard, the version number, which will be represented as a little Indian encoded D word. So in this case, today is the version 1 that is implemented. So if you want to create your own first WASM file, well, it's super easy. You just use printf, and you copy-paste the following bytes that I just mentioned. And you've got your first WASM file. Hooray. And following the header, you've got sections. And all sections are going to dictate, just like any other format, such as file format, such as ELF, they're going to dictate how the binary, the module, the WASM module, is going to be manipulated. And the header must have an identifier, which is an integer, that will state the purpose of the current section. And following the identifier, you can have optional information, and then the body, which is the actual content. And which identifier do we know? Today, there's 12 identifiers implemented, and they cover everything that kind of makes sense when you're defining a new file format. So you've got a code section, you've got function section, you've got global, you've got one dedicated for the memory, and so on. An interesting one is the ID equal to 0, which is the custom one. And as you can see, the ID is 0. So it's kind of showing that WebAssembly, once again, was meant to be extended, extendable and extended in the future. And today, you can already use those custom sections. So we'll cover a little bit we'll dig into a little bit those sections. Actually, only the most interesting ones. I'll start with the function section. The function section is going to define all the signatures of all the functions inside the module. So when you've got let's say a C file which will have a function compute pi, Fibonacci, and all that, we want to expose that to WebAssembly. Then when you're going to be compiling the code, the compiler will generate the function section that holds that will be nothing more than a table with the type and number of arguments, parameters that this function takes, and also the number and type of the value, of the return value, sorry. And everything will be stored in a table and assigned to it an index. And this index is extremely important because, as you may remember, I mentioned that there's no pointer in WebAssembly. That means that what happens when you want to call a function, you can't call a function just like what you would do in any other file format. But instead of that, you will be calling an index to this function. And that provides a huge advantage, which is it's going to allow the loader, when it's going to be parsing the WebAssembly code, to check, okay, now I've got two arguments that are trying to be calling function at offset, at index 0. Do I have such index? Yes, no. And if I do, I know exactly the number of arguments this function is expecting, and also what's going to be returned. So that's going to be killing a lot of possible kind of control flow hijack. A few extra sections that are important. The export and import will respectively be responsible for showing the WebAssembly functions from the WebAssembly module to the outer world. So it can either be a WASM module, or it can also be the JavaScript engine. You can call a WASM function directly from JavaScript. And the import, it's the other way around. It's going to allow JavaScript function or JavaScript pointer and object to be passed to the WASM VM. Start section is pretty much self-explanatory, and global section will hold all the global variable, again, assigned to it and stored by index. So that might be a little bit abstract. So let's go for a quick demo of what WebAssembly actually is. So here, I don't know if you can see, that might be better. Okay, so I wrote this hello shakaCon WASM file. So the format is called sexpression. It's a little bit similar to Lisp for those who know. This will be the native format that you will be able to write WebAssembly code in. But there's a much easier way, as we will cover. And here, as you can see, we've got this module, this new WASM module, that will be importing a print function from somewhere. And this print function, I have to declare what it looks like. And in this case, it will take two parameters and won't be returning anything. And it has a memory because the data has to live somewhere. And in this memory, I'm going to have I'm going to store a string that is hello shakaCon. And all my function main is going to be doing in this case will be to call the print function, which is coming from somewhere. At this point, WebAssembly engine doesn't know at all where it's coming from. And when the function main is which is noted as exportable, as you can see, when it's being called, it's going to be looking up for inside the memory section at offset 0 and printing 15 bytes from there. So you can use the WebAssembly toolkit to compile the code. And once it's compiled, you've got your first WASM file, which looks something like this. So it's not really easy to understand, easy to manipulate. So what I've done is I've created a Kaitai parser. If you don't know what Kaitai is, then what is going on? Do I have internet? Okay, that's weird. Okay, we'll get back to this demo. I have to move on. So yeah, part of this research, I had to create some tools because a lot of tools that were already existing were not sufficient. And yeah, I will all release the tool at the end of this presentation. So yeah, time for a live demo. Apparently, things can still go wrong. So how will you be able to create your C file and inject it into your browser? That's the most interesting part. And that's where we introduce a lot of tools, and the most interesting one is the mscript10. mscript10 is a toolkit. It's a bunch of tools that are going to allow you, that will provide a compiler that will generate WebAssembly code directly from your C code. And I'm not going to go too much into the details, but the way it's going to look like is going to take your C code, transform it, and output, as you can see, the WASM code. But it's not the only tool that is capable of doing that. Not earlier than last April, Go decided to integrate WASM as a valid file format. So soon in the next release of Golang, you will be able to create your Go file and then simply build it using Go, just the same way as Rust is already capable of doing. For the building tool, when you want to create your WebAssembly code, I would highly recommend to check out the WASM Studio, which will help you greatly when it's a free online IDE to build WASM stuff in different formats, whether C or Rust. And the second one I would recommend is the WASM Explorer, and because it has this very interesting property that when you input C code, it will also not only generate the S expression corresponding file, but also the native code that will be executed, that will be generated from, in this case, Firefox WebAssembly engine. So you can actually have a visual representation of what your WASM code is going to be looking like inside a browser, which I find pretty cool. And again, part of this research was also creating the tools that did not exist yet. And one of them was, what was missing and what I thought would be interesting was to build an IDA loader and processor, which I did. So yeah, they will all be released after this talk. If you guys are interested in decompiling in IDA your first WASM module, then you can do that. So now we know how to transform our C code into WASM code. How do we load that into the web browser? Well, the problem here is that the web browser has no idea of what WASM is. It's not a valid MIME type where the web browser is just going to take the WASM code and magically execute it. We need something to load it, and that's where JavaScript comes in. The way it's going to work is at some point you will need to provide to your JavaScript engine the WASM code, the WASM module, as an array buffer. This can be done in two ways. If your code is small enough, by small, it means less than 4,000 bytes, or 4,096, then the code can be inlined. That means that you can literally create inside your JavaScript code, you can create the code manually inserting the bytes one by one, which makes it really convenient if you're trying to fuzz WebAssembly. We'll cover the fuzzing part a little bit later. And the second part, which is the one that is recommended by the MDA and by Mozilla, it's to use the ECMAScript 6 promise functionality. So the promise functionality is going to allow you to create some asynchronous events in JavaScript and trigger some functions based on the response to those asynchronous events. So in this case, you will call a function that is implemented called fetch to grab a file. This time will be a real standalone file called hello world or whatever. And the result of this fetch function will be to provide an array buffer. So we will it will be to provide the stream of byte that we will convert into an array buffer. At this point, we've got inside our JavaScript engine an array buffer containing our WASM module. So we need to invoke the WebAssembly.module on this code, on this array buffer, to have the JavaScript engine validate the file, the module that we're giving to it, and making sure that it syntactically makes sense, that we've got all the functions, all the sections appropriate. For example, make sure that if you've got a code section, you need to have a function section and other checks like that. And finally, one of the last things that this module function will do is to JIT the code. And that's the part where, after the validation, it's going to create native code. So now the code is in memory. It's in a totally different location, which is not writable anymore. So we're ready to go. All we need to provide is to provide our code with a simple memory. With the memory is nothing more than a number of pages that are being allocated. As you remember, a page in WebAssembly is 65,000 bytes. It's not like a regular page for an operating system. So we're going to be creating a memory section with n number of pages. And then we'll declare all the elements that we want to pass to the WASM environment. So if you remember the code, we decided to pass a function. Well, the code was expecting a function, was importing a function that was coming from a library called stdlib, and the function was called print. That's where we're going to be creating those objects and passing them to the WASM VM. And at this point, everything is done. So all we need to do is instantiate the VM. So ignite the whole thing. And now we've got our WASM engine that is fully working. And we can, via the export property, we can directly invoke all functions that are marked as exportable, as we saw in the WASM example. So if we go back to our first failed demonstration, so to make it a little bit more clear, so I created a very simple loader, which is exactly going to be doing what was explained earlier. So here we've got a log function that's going to be reading some data from the memory that will be given to the WebAssembly VM, and will read a number from an offset and a certain number of bytes, encode that to UTF-8, and then alert the string. So again, as you can see, it's not WASM, it's not WebAssembly that's doing the interactional part. It's left to JavaScript. Then we initiate the memory and provide this, and then ask for the module to be loaded in the main function. Once it's loaded and put inside an array buffer, a JavaScript array buffer, we instantiate it, and then we call the function main. And so now we've got a JavaScript engine. The only thing that we need is to have a simple HTML file, which could be as simple as this. And if we decide to fire it, we've got our work. Yeah, so I don't know if, no, it doesn't work. Yeah, it does. Okay, so we've got this pop-up, hello Shaka Khan, that is being displayed. So interestingly, the alert is being sent by JavaScript, but the code from the actual function call was done in WebAssembly. So yeah, we've got our WebAssembly file, a WebAssembly working module. So okay. And what I will show next is you can also use mscriptem to compile directly from C directly into the web browser and make it a lot easier. So magic command -s. And similarly, we've got, again, hello Shaka Khan. So something that I forgot to do is actually to show you what the C file looks like. It's literally the simplest C file that you can think of. But what it means from now is that using EMCC, so mscriptem compiler, you can use your C code, do a little bit of modification to it, and then compile it to have something that works in your web browser. So if you saw this tweet that was from last week, I believe, about Vim being ported to WebAssembly, that's exactly what they're using. And last, what I want to show you is also the fact that the code is being JITted. And to do that, we're going to be using D8, which is the JavaScript command line tool that is provided by the Chrome engine, by V8. oops, no, we're not going to be running GDB. So D8. Yep. Okay. So first, you can see that the code has been executed because we've got hello check account being displayed. And then if we go up, we can see the code, the WebAssembly code that is being generated. Here, WebAssembly code. So from that moment, it means that the JavaScript engine, well, the WASM engine, has all the way to optimize the code and make sure that not only the code, the WebAssembly code is valid, but when it's generated, it can also optimize it once again. So it provides a lot of way to improve the performance. And so as you can see, what you're going to be executing is native code, which now explains a lot better the performance that we had when we were testing this on SHA. So now let's cover the attack surface. Because, as usual, with great power come great responsibilities. Here, what's interesting is that the security was in mind of the developers from day one. If you go and check out the specification, you've got a whole section dedicated to the security. Even before starting coding anything, they had in mind two things. The first one is we want code to be able to execute in a contained environment. So there's two properties. The first one is we want this code to be safe. So when this code is being executed, we don't want it to be conflicting with any other code that is going to be executing. So it's safe in itself. But it's also safe from the inside out. So you've got a WebAssembly code that's going to be executed. You don't want it to be messing with your JavaScript engine and so on, unless specifically designed to do that. So if you decide to share an object, well, by design, you allow this this communication between the two objects. So the code is strictly sandbox, it's strictly isolated, and they had some notions in the specification that are quite innovative, in my opinion, because quite recent. So immutable code, obviously, but the separated stack is something that is defined in the standard, in the specification, where you're going to have a totally different stack that will be used for the user data and the control flow return addresses. So forget about all the vulnerabilities like Stack Overflow or something like that. Even if you have a Stack Overflow, it doesn't mean that you're going to be able to control the, or to hijack the control flow. So that's a big win. And when I saw that, I was very surprised. So I was thinking, yeah, finally, apparently web vendors have learned from the past. That's really, really good. So I was quite excited about WebAssembly. So I started, after reading the specification, I investigated the implementation, different implementation in the major web browsers. And I realized that, okay, if the specification kind of tightens the security of WebAssembly, the problem won't necessarily be there. The problem will be in the implementations, because all the implementations will be in C, C++, which, as we all know, are affected by all kinds of badness. So that would be the first place to have a look at. And as a matter of fact, a bunch of people have come to the same conclusion in the past, and there's a lot of issues, well, a lot, not that many, but quite a number of issues on WebAssembly. The most interesting one for me was the CVE 2017-5116, which was used in the full chain compromise of the Google Pixel. And they actually used WebAssembly to break out of the environment. What they did is that they abused the fact that, as we saw together, you can use the memory as an array buffer when you're using it as when you initialize it in the WebAssembly part of the, well, in the initialization part of the WebAssembly module. But what you could do, I insist on could, is that you could also back it with a shared array buffer. And a shared array buffer will allow two concurrent threads to be modifying on the fly the code or the memory section that is being or that was very recently checked. So you've had here a race condition, because what they did is they spot a very specific point in the code that was calling a function at index 0, right? And so at this point, you had another thread that will be racing and constantly hoping to overwrite the index. Instead of calling the function at index 0, which exists and is valid, we'll try to call a function at another index. So it's a race because it had to be done right after the validation, but right before the time that the code is being converted to x86. So it was quite awesome, but if successful, and it was successful, then you had an arbitrary read and write into your whole JavaScript address space. And it's a very powerful vulnerability. The problem is, as you saw, it was using shared array buffer. But last January, thanks to Meltdown and Spectre, well, in this case Spectre, all web browsers have decided to ban shared array buffer. After 1 year of implementing it, they finally realized it's a bad idea because all the exploits in the world were using it. So they stopped the damage and at least disabled it by default, and in some cases they removed it for some web browser. So yeah, it was definitely an interesting case, and for me it kind of set the bar of where the possible vulnerabilities that we can be leveraging via WebAssembly will be coming from. This is not a vulnerability from the specification itself. It's a vulnerability in the implementation. So I've decided to review all the major web browser JavaScript engine and WASM engine looking for code. And the code was not surprisingly that big because, again, I think it's coming from the simplicity of WASM. The code doesn't need to be really, really huge. And after about 2 weeks of fuzzing on different, on all the JavaScript engine, I started to have some crash with GSC, which is the command line tool from WebKit, which is used by Safari. So I was like, yeah, finally I'm going to be able to do some fun stuff with WebAssembly. And in about 2 weeks, I managed, about 2 weeks of fuzzing, I managed to trigger approximately 30 different bugs on using different mutation strategies and different fuzzers as well, different fuzzing technique. So I was really excited. But when I started having a look at the code, then I realized that it's actually, the code in JSC was actually killing itself on purpose when it started decoding a WebAssembly code that is not valid. So instead of risking the fact that they're going to be executing something that is unknown, well, Safari is doing nothing more than a huge harakiri and killing itself. So I was very disappointed at that moment, but it was a good news because it means that what happened is web browsers, vendors, they've learned from the past once again. So WebAssembly was massively tested, and the testing code for at least Edge and Chrome are available publicly. So you've got those AFL and libfuzzer script that you can start playing with and start running your own fodder with. So again, very positive thing. It's not a bad thing. And for me, that comes from the fact that the whole concept of WebAssembly was secure enough. It was simple enough to be easily securable. So what else could we have a look at? So yeah, there's some other issues, right? We've got a way to allocate up to 4 GB in the address space of the JavaScript engine. So the first attack and stupidest attack that you can think of is a simple denial of service. You're going to try to simply overwhelm the memory of the machine by trying to allocate different modules with a lot of memory. Another vulnerability would be arithmetic error and race conditions. Interestingly, to this day, there's still a very interesting arithmetic error that exists in the Safari engine, where they don't compute properly the way how you can grow the memory of the WebAssembly engine. And what happened is that if you decided to have the size of the WebAssembly VM being equal to 4 GB minus 1 page, you have an access to this whole address space, right? So you can start writing memory in a little bit everywhere. This is the intended way of working. But then if you decide to grow the memory by just one page, then you're going to be hitting the 4 gig of the 4 gig limits. And interestingly, instead of saying you've got 4 gigs of memory now, the WebAssembly engine of Safari will say, well, now you've got 0 bytes in your VM. So everything that you've been writing in this memory is now lost. So funny bug. And on the offensive perspective, what could you do with WebAssembly? WebAssembly is perfect for side channel attack. It's the dream, because you literally can have native execution being done in your web browser. So you can have very precise way of doing some caching attack. Problem is, now it is much harder because of the Spectre mitigation. You can also use the WebAssembly for obfuscating things and then just have a huge eval that will, for example, call, I don't know, some XSS exploitation tool, and bypassing all the WAF of the planets. And for me, one of the worst case of use for WebAssembly is crypto mining. Crypto mining here, what we've seen so far is stuff like CoinHive, where you're going to have very poorly written JavaScript code that will be trying to run code and mine on users' behalf, trying to get some money out of people visiting a targeted page. But here you have a way to execute the same code, but much faster. So that what it means is that now attackers or even just people who wanted to make a little bit of money from their website have the possibility to execute code on your behalf, on your machine, and use some computational resource so that they can, I don't know, maybe purchase a better server or extend their SSL domain or whatnot. And there's already a few open source variants spotted in the wild. Those tools are on GitHub, so feel free to check them out. And once you are in the WebAssembly code, my question was, what can I do? So the second property, if you want, from the security section was I cannot do anything to go from inside the WebAssembly code outside. Yeah, okay, but I can still execute code. I can still execute C code. So all the vulnerabilities like buffer overflow will still work. I won't be able to exploit them the same way because I won't be corrupting the stack and I won't be corrupting the return address the way we normally do. But I will still be able to have a buffer overflow, so that still counts. And also format strings attack are still there as well. You have ways to leak pointers and information from the WebAssembly VM. So it's not really bad in itself because you can't go anywhere else. It's not like you can use this information and say, okay, you have defeated ASLR on JavaScript. It doesn't work like that. But still interesting to know. And for the defensive part now, so WebAssembly is not a huge threat in itself, as we saw in this presentation. But if you decide to disable WASM, then only only Firefox and Chrome allow you to do that today. Maybe Edge and Safari will decide to do the same in the future, but with just a couple of flags, you can disable that. And if you're working, if you're a blue teamer and you're just trying to detect what's going to happen, when you're, if you're just trying to detect that WebAssembly code is being downloaded, for example, people are playing video games or crypto miners are being played on the network, well, you can simply try to look up for the flag nullbyte ASM. It's a unique flag, so you can be sure after that that the code will be WebAssembly. But other than that, it's pretty hard to audit. That's why we decided to write a bunch of other tools to, mostly the IDA processor to mitigate that, which comes as part of the static analysis part. But complex project in the future, because WebAssembly, again, is here to stay, complex project will be using compilers because, again, they will try to be running code as fast as possible and using as many features as they can. And they won't spend a lot of time re-implementing the wheel. So they will use tools like mscriptm. Mscriptm is super heavy. It's going to be generating big fat files. and that those files are easy to detect if you are trying to build AV signatures. But other than that, once you've got the once you've got the WASM file, you're going to be facing the problem that the understanding it's quite hard. Again, interestingly, I saw that the PNF software company released a full decompiler for WebAssembly as part of their toolkit. So that could be one of the possible ways to analyze better the code. And so we're close to the conclusion now. The future of WebAssembly, because yes, there will be a future. WebAssembly is here to stay, and there will be more versions. We won't be staying in the MVP 1.0 for very long. As a matter of fact, the next steps of the improvement of the specification are already underway. And on this list, we can see that it's already being implemented. So some of the browsers that we use, for example, Firefox, if you're using the bleeding edge and so on, the nightly builds, then some of the features that are going to be added to the specification in the future are now in beta test in the web browsers that you are probably using. And not everything is good. Some ideas are definitely, will be interesting to check for possible implementation error. Most likely, they've decided to add kind of a mmap mechanism, so asking for memory on demand, and that comes with a whole lot of problems when it's going to be finally implemented. And on top of that, they want to add some kind of permission mechanism. So again, how WebAssembly is going to be dealing with that? Is it going to be a unified way dictated by the specification, or is it going to be implementation specific? We can't know now, but it's definitely the kind of thing that are interesting to keep an eye on. As of today, there is no multi-threading. So all the code in your JavaScript, in your web browser that is executing WASM code is running on one thread. So again, there is no risk for possible race conditions, thread-based race conditions, because they just don't exist. And that's something that is actively implemented right now, at least on Firefox. So yeah, it's going to be interesting to see what the future keeps for WebAssembly. I will definitely keep an eye on it. So I hope I didn't make WebAssembly too boring. I was very interested in this research because it gave a lot of opportunity to dig into some two universes that don't talk to each other normally. So you've got the web universe and the more lower level part. So it was definitely interesting to have a look at, and mostly because WebAssembly is not going anywhere. It's implemented, it's functional, and more web developers, developers are turning their application into WebAssembly because there's a huge potential of finally having some code that being executed at a very high performance and in a unified way. So that's something very unique, and that will solve a lot of problems. But again, we need to keep an eye out on every single new release that will come from the newer implementation of WebAssembly, because they can bring some new bugs. So I will leave with just a bunch of links if you're interested for having a look and playing by yourself with WebAssembly, and it will be the end of my presentation. Thank you for listening.